Hello, my name is Blaine Hatcher, and this video is for the Physics Media Review Project. This is focusing on the Tiger Tank battle in the 2014 film Fury. While this movie is a nice watch and has good character drama, there is a number of historical liberties taken that are based on outdated and misinformed notions about the US and German armored vehicles. This mainly focuses on the M4 Sherman and the Panzer VII Tiger I, or Panzer VI Tiger I, my apologies. We will be focusing on two particular parts of this scene. This one, and this one. Both of these scenes defy the laws of physics by incorrectly portraying the performance of the Sherman's gun and horribly exaggerating the performance of logs as applique armor. We'll start with the first shots shown, as there is a lot more math involved. But don't worry, I'll get into the second scene. To begin, I will introduce the formula used for armor penetration, known as the Krupp formula. Now, this was usually used for ships, but for our purposes, tanks are like land battleships, so let's get started. First, let's lay out our formula. We have B equals V times the square root of P over K times the square root of D, where B is the armor penetration value in millimeters, V is the velocity of the shell in meters per second, P is the shell's mass in kilograms, and D is the caliber of the shell in millimeters. K is special, because K is the resistance constant. This is a value which regards armor quality and the shape of the shell, but for our purposes, we'll be using the average value, which is 2400. We will assume we are using the M62A1 APC-BC shell, as this was the standard anti-tank shell for the 76mm M1 gun that the Shermans used. If we plug in the values from the documentation, we get 0.1005, which we can round up to 0.101. This is our armor penetration in meters, so when converting that into millimeters, we get a total armor penetration of 101 millimeters. When we compare this to the side armor of the Tiger, which was 80 millimeters, we see that the shell should have gone through and destroyed the tank. However, using the muzzle velocity from the velocity tables would give us a wrong answer for the situation, as that is the velocity as the shell leaves the gun. We need to find the velocity of the shell at the range of this engagement. While we could guess the range from this scene, I'm going to use the one that the Tiger's commander had called out earlier. This is close range for tanks, but this will help us in finding out how the velocity changes as the shell travels. For this, we will use a exponential decay formula, which will help us find out the shell's velocity after 700 meters. While drag is one of many actions that will affect the shell in flight, we will only be taking drag into account for the sake of simplicity. Our equation is as follows. Vx equals V0 times e to the power of negative k times x, where V0 is the velocity at 0 meters, which we will use our muzzle velocity as. M is the projectile's mass, which is 7.07 kilograms, and x is our range. K is our drag constant, which we need to calculate using a different formula. This formula is rho times CD times A divided by 2 times M. Rho is our air density, which is 1.225 kilogram per cubic meter for calm sea level air. CD is our drag coefficient, which we will plug in the value 0.3, since that is the normal average for a shell-shaped object. A is the frontal area of the shell, which is 0.00456 meters squared, equal to half the diameter in meters, and M is still our mass. Plugging in our values gets us 0.000118 per meter, which we can now plug into our drag equation. This gives us a 7.383 value, which we can translate to 738.3 meters a second. If we plug this velocity into the Krupp formula from earlier, we get 0.093, which translates to 93 millimeters of armor penetration. We now know that even at the range they engage at, the Tiger should be destroyed. But math isn't perfect. Due to the angle the shell strikes the Tiger, it ricochets. This is because it strikes at an angle, and it is because of this angle that the Tiger's armor has a higher effective thickness than the shell can penetrate. Without going into too much detail, armor at an angle is harder to penetrate because a shell going in a straight line has to go through more material if the armor plate is angled. There's also an equation for this, which is as follows. TL equals Tn divided by cos x. TL represents effective armor in millimeters, Tn represents the actual thickness of the armor in millimeters, and x represents the angle of the armor in degrees. We'll plug in 45 for this engagement because that seems right. With the 80mm side armor of the Tiger, we get an effective thickness of 113.1mm. And when we compare that to the 93mm of penetration that we had gotten earlier, we find that this shot in particular does not break the laws of physics, actually. So, you may have one thing on your mind right now. Did we just disprove the premise of this video? No. While yes, the first shot does obey the laws of physics, this next one doesn't. Strap yourselves in, because I'm about to tear this scene apart. There's no plausible way that Fury should have survived this, unless the Tiger was firing a giant Nerf dart. The Sherman had 38mm of armor on the area of struct, but because it's implied that the logs helped to stop the shell, we'll add 20mm of armor, just to be generous. Due to the extremely close range of this engagement, we'll also not be worrying about how the drag will affect the shell, but because the effects that would have on armor penetration are negligible at this range. With that being said, if we plug in the values of the 88mm KWK36 that the Tiger 1 uses, we get 0.10965, which is equal to 109.7mm of penetration. Yet no. Unfortunately, I don't think that Brad Pitt and his tank crew are going to be surviving that if this were actually real life. But this is a movie, and plot armor is impenetrable unless the movie needs you to die. So, make it out what you will. I would like to thank Olivier Barthelemy for assisting with this script, and you for taking the time out of your day to watch my video. Have a great day.